Hello, and welcome back to another week of supervised learning. So far in this course, we've considered a wide range of parametric modelling techniques, with a focus on the linear model and its many generalizations. In the case of only a single predictor, these models describe the conditional mean of the response as a scaled and shifted version of the raw predictor value. That's to say, the conditional expectation of our response has been a linear transformation of the predictor value, or values in the case of multiple predictors. We've actually already considered some non-parametric modelling techniques within the course. For example, basing the response on those of our k nearest neighbours within the predictor space, and using regression trees to predict our response values. This week we're going to move on to consider more flexible models to describe the conditional mean response value using non-linear functions of a predictor. We'll present these ideas in the context of regression, but as we've seen many times already, the regression and classification problems are closely linked. So, with some light adaptation, the same techniques that we develop here can be used, for example, to model the probability of belonging to each classification group, and then pass through some thresholding function to lead to a classification model. The flexible regression techniques we'll develop this week are useful when we have a non-linear signal within our data that we wish to capture within our model, but we don't have any particular reason to specify a specific parametric form for that relationship. The whole topic of non-parametric regression is huge, and we couldn't possibly cover it all in a single course, never mind a single week. So what we're going to do is focus down on three particular types of non-parametric regression, namely polynomial regression, the use of orthogonal polynomials, and the use of regression splines. To give you a flavour of what else is out there, we'll also spend a little bit of time overviewing some other non-parametric methods. So before we get into when we might want to use these flexible non-parametric regression techniques, I'm first going to highlight a case where we might not want to use these. An example of such a scenario is when our data has a nonlinear dependence on a covariate, but we've got a good idea of how to express that nonlinear relationship parametrically. For example, if our data described a lab experiment in which a mass is attached to a spring that's stretched and then released so that the vertical displacement of the mass can be recorded over time, then in an idealized mechanical system, this vertical displacement at time t would have the form y of t is equal to a times the cosine of omega t plus phi. Here a is the amplitude of the oscillation, omega is its frequency, and phi is its phase shift. Don't worry if this isn't something you've seen before. The key idea here is that we have some underlying model that gives us a strong parametric relationship that we believe to be true. In this particular situation, we might use a model of the form yi is equal to beta 1 times the cosine of beta 2t plus beta 3, all with some additional noise added on to each observation, here denoted by the epsilon I. We could then estimate the model coefficients, the betas, using least squares, and if we additionally assumed a particular distribution for the error terms, then we could equally use the method of maximum likelihood here. In either case, we've got strong beliefs about what parametric form the signal within our data should take, and we're using this to guide our inference. Alternatively, we might be trying to model the dynamics of a more complex system. If we don't have strong beliefs about the parametric form that our signal should take within our data, then we might be better off by using a very flexible model, and then letting the data itself determine the form of that function for us. This approach lets the data speak for themselves, so to say, but it doesn't guarantee that there will be enough information within our data to produce a model that is sensible in context. These non-parametric regression techniques that we'll introduce this week can also be used to describe complex covariate effects, and also to describe some types of structured data. For example, by using time or location as our covariate, we can construct very flexible models for the conditional mean of a time series or a spatial series. The figures here show two cases where we might consider using a non-parametric regression technique. In the upper pane, we're considering an example of a nonlinear effect in the covariate domain. We're going to need a nonlinear effect to describe how chemotherapy dosage affects the probability of a patient going into remission, because at very low doses, there's no effect from the drug. In the central regions, there are a range of higher doses with varying degrees of benefit, but then if the dose is made too large, then the chemotherapy does more harm than good, and the probability of a successful outcome for the patient decreases once more. This relationship doesn't have any obvious parametric form, and so letting the data decide is potentially a good approach here. In the lower figure, we've plotted the acceleration of a crash test dummy over time during a motorbike collision. At the beginning, the motorcycle is travelling at a constant speed, and so the acceleration is 0. Then there's a period of rapid deceleration by a series of smaller and smaller recoils. We might want to model this using a damped version of the harmonic oscillator that I mentioned just before, but we might also want to compare that to a more flexible model as well, since there are many more features in a car crash that we potentially aren't capturing. This situation is far more removed from our idealised mechanics than our mass on a spring was. This data example gives us one instance of a nonlinear effect in the time domain, and if we consider time as a covariate within our model, then we can equally consider these two problems in a single framework. An added bonus here is that it gives us a way to model data that are structured through time, but don't meet that equally spaced measurement requirement that is intrinsic to so many time series models. A quick note here on this second dataset. You may see this in many different examples of non-parametric regression techniques, and that's because this dataset, originally from a paper by Silverman, is used analogously to the iris dataset in terms of classification. It's used as a very nice toy example on which to demonstrate techniques. So how exactly are we going to go about modelling these nonlinear relationships between covariates and responses? The first approach we'll consider is polynomial regression, and here I'll just introduce the core idea of it. Within our data, we have two components. We have the signal, f, which is a function of our covariates, x, and some additional noise on top of that signal. In all of our previous modelling attempts, we've been approximating f by some linear transformation of that covariate value. Sometimes there's a good reason to believe that this is the case, but often there's not. So what we can do instead is generalise and assume that the function f is an analytic function, so that at any point its Taylor series converges to the true function value. This is what we're considering in the equations at the top right of this slide. We can approximate this function f as well as we like by taking an infinite weighted sum, where each term is raised to a progressively higher power. If we were to expand out all of the brackets here, we can write this equivalently as saying that we can approximate the function f as well as we like using a polynomial, as long as that polynomial is a high enough degree. Of course, working with infinitely high dimensional polynomials is difficult to do in practice, so what we do is replace this by an approximation, and say that if we take a high enough value p for a number of polynomial terms, then this is going to give us a good approximation to our function f. What this means is that we're using a polynomial basis for our analytic functions. We're describing any analytic function as a linear combination of x to the 0, x to the 1, x squared, x cubed, and so on. And we're making the approximation here by cutting that off at p plus 1 terms. We can then incorporate this idea within a regression by creating a series of predictors that correspond to our original predictor raised to each of these powers. So here, our first column corresponds to x to the 0, our second column corresponds to x to the 1, third to x squared, and so on all the way up to x to the p. We can then use this design matrix to perform linear regression, but this allows us to represent nonlinear relationships between the predictor and the response, but using a linear model form. One issue that we have here is that we don't actually observe values of f at each data point. We see noisy observations with that additional noise term included. What this means is that as our polynomial degree increases, as we increase the number of basis functions that we're using, we aren't actually going to converge to the true function. We're going to end up overfitting to our data at some point. We're going to start modelling that noise as well as the true signal. This presents us with a trade-off between bias and variance here. So in this example, for the motorbike acceleration, we can see that as our polynomial degree increases, we're getting a closer and closer fit to our training data. Increasing the polynomial degree too much is going to lead us to overfitting and our model not generalising well to new situations. This is something that we've dealt with many times before by now, and boils down to picking that number of polynomial bases, so the value for p, using cross-validation to determine which will have the best generalisation properties. And a final issue to be watching out for here is that our true signal might not actually be an analytic function, in which case we're going to have our infinite power series converging to something that still belongs to the set of analytic functions that best describes this non-analytic function plus the noise. So let's return to this idea of the design matrix for polynomial regression once more, and consider the quadratic case, which was the curve shown in green in the previous plot. In this case, we have three terms within our model. We have an intercept term, a time effect, and a squared time effect. And the size of these relative to one another is determined by our model coefficient beta 0, beta 1, and beta 2. This simple form for the design matrix gives us a model that is really easy to implement and relatively easy to explain, at least at low orders. When it comes to explaining the effect of t to the 5, however, things become a little bit more complicated to try and think about. One downside to this approach, however, is that the estimated coefficients, so the values for beta 0 hat, beta 1 hat, and beta 2 hat, are going to be very highly correlated with one another, and that's what's shown in this correlation matrix here. We can see that our off-diagonal terms are very close to 1. This means that even a small change in the estimate of our linear coefficient is going to lead to dramatic changes in our other coefficients, and potentially our function overall. A second downside to this approach is that the polynomial functions that we're using as our basis don't have localized effects. Every data point, no matter its t-value, is going to influence every model coefficient. This isn't necessarily desirable because we might want to be able to tweak the fit of the function at one end of the covariate domain while keeping the fit as it is at the other end. A partial solution to these problems is to use what are known as orthogonal polynomials. Really, we've made a very arbitrary decision here to use x to the 0, x to the 1, x squared, and so on as our basis polynomials to describe the entire space of analytic functions. We could have picked a different set of polynomials, which here I'm calling p0 through pp, to use as our basis functions instead. And the trick here is that we're going to choose these polynomials, and this should say p0 to pp, such that the columns of the design matrix X that they produce are orthogonal from one another. How exactly to go about this is far from obvious, but fortunately we have good software implementations of these things, and for those of you keen on linear algebra, this is related to the Gram-Schmidt orthogonalization process. The benefit of using this orthogonal polynomial basis is that the coefficient estimates and uncertainties are now independent of one another. They're unchanged by changing the values of other coefficients. And in particular, what this means is that they aren't going to change as more polynomials are added. This has solved one of our problems about the high degree of correlation between our parameter estimates, but it hasn't fixed the problem that our orthogonal polynomials still have infinite support. They're still defined over the entire time or covariate line. So to summarise what we've covered here, we've introduced the idea of polynomial regression as a linear model that allows us to describe non-linear relationships. It's linear in the model coefficients, but non-linear in the predictor values. This technique leads to highly correlated coefficient estimates and uses basis functions, basis polynomials, that have infinite support. We then briefly introduced the idea of orthogonal polynomials, which resolve this correlation issue, but leave the support issue unchanged. Calculating these orthogonal basis functions is not straightforward, but can be done reasonably efficiently, particularly when you have evenly spaced observations. And finally, as a quick teaser for what we'll be covering next time, we'll be looking at how we can use a different set of basis functions with a finite support in order to get around this issue that's inherent when using a polynomial basis in a non-parametric regression. Thank you very much, and I'll see you in the next video.